Hello everyone, my name is Vidyanand. My roll number is 20BQ1A04G4 and I am from ECEC section. Now I am going to discuss about semiconductors. Before going to the concept of semiconductors, one must know why they are known as semiconductors and the properties of semiconductors. Let us know the properties of semiconductors. We know that matter in the universe is classified into three types. They are solid, liquids and gases. To understand the topic of semiconductors, we consider the solids. Solids are again divided into two types. They are crystalline solids and amorphous solids. Let us consider the properties of crystalline solids. In these solids, atoms are arranged in the regular pattern, in which they follow a systematic pattern. They are anisotropic, which means physical properties like conductivity, refractive index, and velocity of sound depend on the direction. They have sharp and well-defined freezing and melting points. These are the properties of crystalline solids. Let's come to the amorphous solids. No regularity in the arrangement of atoms. Isotropic in nature, in which the physical properties like conductivity, refractive index doesn't depend upon the direction. They do not have well-defined and melting and freezing points. Based on the electrical conductivity properties, solids are again classified into three types. They are conductors, insulators, and semiconductors. First, let us consider the properties of conductors. Conductors consist of large number of free electrons, which are not strongly held towards nucleus, which means they consist of large number of free electrons in the outermost shell, which helps them to conduct electricity. Examples for conductors are gold, silver, copper, and aluminum. They have high electrical and thermal conductivity and low resistivity. They have positive temperature coefficient, in which resistance is directly proportional to temperature. They obey Weidmann-Franz law, in which the thermal and electrical conductivities ratio is directly proportional to temperature. Secondly, coming to insulators. Insulators have less number of valence electrons. Valence electrons are tightly bound to the nucleus. No free electrons are present. Example for insulators are glass, mica, quartz. They have high resistivity and low conductivity. Thirdly, coming to semiconductors. These substances have conductivity intermediate between conductors and insulators. Their resistivity is higher than that of a conductor but lower than that of an insulator. They have negative temperature coefficient, in which the resistance is inversely proportional to temperature, in which we obtain an expression R equal to A into e power minus B by T. R is resistance of the semiconductors, where A and B are the constants. Origin of energy bands in crystalline solids. When we consider an isolated atom, we have different discrete energy levels like 1s, 2s, 3s and so on. If we consider a solid, we find n number of atoms correspond to the n different energy levels. The collection of these energy levels of the atoms in the solid is known as energy band. Valence band. Energy occupied by the valence electrons is known as valence band. Conduction band. Electrons which have left the valence band are called conduction electrons. The band which is occupied by the electrons is known as conduction band. Forbidden energy gap. The gap between the top of valence band and the bottom of conduction band is known as energy gap. Valence band. Energy band occupied by the valence electrons is called valence band. Conduction band. Electrons which have left the valence band are called conduction electrons. The band which is occupied by these conduction electrons is known as conduction band. Forbidden energy gap. The gap between the top of valence band and bottom of the conduction band is called energy gap. It may be large, small or zero. It depends upon the material. Let's consider for conductors. In this, valence band and the conduction band overlap with each other, which results in the no forbidden energy gap. At room temperature, conductivity is high for conductors. Example for conductors are metals. Semiconductors. In this, valence band and conduction band is separated by forbidden energy gap. Forbidden energy gap is in the order of 1 electron volt. At room temperature, conductivity is intermediate. Best example for semiconductors are germanium and silicon. Coming to insulators, valence and energy conduction band are largely separated. Forbidden energy gap is in the order of 6 electron volt. No conductivity at room temperature. This means there doesn't show at room temperature there doesn't show any conductivity. Example for insulators are rubber and glass. Based on the impurity level of the semiconductors, again the semiconductors are classified into two types. They are intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductor. Intrinsic semiconductors are also known as pure form of semiconductors. A semiconductor which is in the pure form is also called as intrinsic semiconductor. Example, silicon and germanium. These form covalent bonds with neighboring atoms. Due to the valence electrons are tightly bound, so they have low conductivity. At low temperature, valence bond is filled with electrons and conduction band is empty. Hence it acts as an insulator. At high temperature, covalent bond breaks. Intrinsic semiconductors. Intrinsic semiconductors are pure form of semiconductors. They are called intrinsic semiconductors. Example for intrinsic semiconductors are silicon and germanium. These form covalent bonds with the adjacent neighboring atoms. Due to that, valence electrons are tightly bound, so they have low conductivity at room temperature. At low temperature, valence bond is filled with electrons and conduction band is empty. Hence, it acts as an insulator. At high temperature, the covalent bond breaks and the valence electrons in the valence band get excites to the conduction band. As a result, in the valence band, a vacancy is created. The vacancy of the electron in the valence band is known as hole. Hole behaves as a positive charge and and the resultant current developed in the valence band is termed as hole current. It is termed as IH. The conduction band, due to the flow of electrons, electron current is produced. It is termed as electron current. It is represented as IE. The total current in the intrinsic semiconductors is represented as IH plus IE. In the intrinsic semiconductors, number of electrons in the valence band is always equal to the number of holes in the conduction band. Now coming to the Fermi energy level. The highest energy level at which an electron can occupy at 0 Kelvin is called Fermi energy level. In the intrinsic semiconductors, Fermi level will be at the middle of the forbidden band. Because of low concentration of electrons and holes in the total current becomes 0 in the intrinsic semiconductors.